Research has too often been done in silos, with great focus on a narrow area of expertise. But through shared knowledge and access to data, wider problems can be solved. From inequality to sustainability, from helping our ageing population to better ways of raising our children. It's that spark of an idea, disrupting what we know. By thinking differently, our behaviour will change. This research is already happening. But now there is a new home in Cardiff that brings it together. A place open to the world that celebrates and encourages innovative thinking, collaborative working, and sharing ideas. The world's first social science research park. Spark. A spark to change our futures.
So good morning, everyone. My name's Kate Sunderland, and I'm one of the business development managers at the CPD unit at Cardiff University. It's really great to have you all joining us this morning, so thank you so much for attending. So this first session on semiconductors is at the start of our second week of second and final week of the CPD summer school, where we're featuring 14 different sessions provided by the university's research centres and institutes. And we've got a really broad range of topics in the summer school, from today's session on semiconductors, so demystifying semiconductors, to things like the power of collaboration, the exciting world of data science, things on the UK creative economy, and that's just to name a few. So just a little bit about summer school before I introduce Chris, today's presenter. So the summer school is something we started back in 2020, not long after the start of lockdown. And this idea came about because we tried to provide something useful to industry and third and public sectors at a time when face-to-face courses and conferences were being cancelled. And it's been so well received over the last 3 years that we've decided to run this annually and hopefully for many more years to come. So whilst we just wait for the final few people to arrive, I'll go through and just remind about some basic housekeeping. So just a quick reminder that this session is being recorded and will be made available on the CPD Unit's YouTube channel, along with all the sessions from this year's summer school and from previous years. So it means that you can re-listen to the session should you wish, and you can have a look at things that you might not have heard about and let your colleagues know by all means about these resources, because they're really great resources to access. In terms of IT issues, so if you've got any problems, technical problems during the session, such as sound, etc., then feel free to make use of the chat feature, and myself or my colleague Jess will try and do our best to assist you. And if your Wi-Fi drops out, then just reuse the link provided and we'll admit you into the session. So just about Q&A. So we'd really encourage questions from you today. It would be really great to get your input into the session. We'll probably aim to take kind of most of the sessions towards the end, but if you've got some really burning questions as we're going along, then feel free to kind of use the chat facility, and I'm sure Chris will kind of accommodate requests and things as we go along as well. So finally, just about feedback. So we'll be sending out a short online questionnaire at the end of the summer school, which is the end of this week. And we're really keen to keep identifying sessions that are of interest to you and would really value your feedback as it helps us plan and prepare for future activities like this. So please keep an eye out for the feedback form. It'll only take a few minutes for you to complete, and we'd be really grateful if you for your time with this. So that's, I think, more than enough from me. And now I'd like to introduce you to Chris Meadows, Director of CS Connected, who's going to help us demystify the world of semiconductors. So Chris, thank you, and over to you.
Thank you very much. And that's certainly the intention, to demystify it. If anyone is familiar with semiconductors already, then obviously it won't be so much of a mystery. But quite often, I think that the whole world of semiconductors is seen as a bit of either a black art or a grey area from outside of the industry. And there's certainly some kind of uncertainty about where the UK and other nations fit into the supply chains, because it is very much global in nature. So thanks very much for the opportunity to be able to present today and to talk about the mysterious world of semiconductors. If you're not aware, or if you weren't aware of semiconductors before about 2020, then I'm sure you are now, because it's pretty much all over the press. And it's not something that I'm really boasting about, but the fact that there is a semiconductor shortage has really brought a focus onto our industry sector in a way that hasn't been seen for about 50 odd years, when semiconductors first made their debut into the digital world. So if you look around, everyone's saying they can't get their cars, their consumer products, because of a shortage of semiconductor devices. And some of this is because of the complex and fragmented supply chains. It's a very complex technology, so it's not something that can be switched on and off very quickly. And there's a lot of history to how the global supply chains work. What may be less familiar is the fact that the UK and South Wales in particular has a very strong presence in the semiconductor world, but semiconductors are not a one-size-fits-all. We're often asked to describe the global semiconductor supply chain, but like many industry sectors, there are lots of sub-industry sectors and lots of different applications and markets and different technologies. So it's not just a single element. And just to give some sort of emphasis to the importance of semiconductors right now, because of the shortage, a lot of countries and a lot of nations are announcing massive investments in order to be able to make sure that they have capabilities to weather future storms in terms of supply shortages, but also to make sure that they own the technology that goes into a lot of other devices and end markets and products that we're all familiar with, from cars to computers to wearable devices, healthcare technologies, and pretty much anything that we touch in our daily lives. The US started by announcing a $52 billion investment over the next 10 years to make sure that it can bring back some of the activities that it lost in semiconductors to Asia. A lot of the semiconductor revolution in the 1960s and 70s started in Silicon Valley in California, but very little is actually manufactured there now, even though there are a number of global headquarters. So Joe Biden was seen waving a semiconductor wafer in his hand, saying we need to bring this manufacturing back to the US. Ursula von der Leyen has made a similar declaration in Europe with the European Chips Act, or CHIP Act, and a commitment of 145 billion euros. Korea, already a strong player, has announced a 500 billion US dollar investment over the next 10 years, and President Xi of China has announced a $1 trillion investment to become less reliant on the US and the West. So everyone's fighting for a piece of the action. And it's not too surprising in some ways, because semiconductors, even though they're often behind the scenes and we don't really, or we're not really that familiar with the industry players, it's actually the fourth largest global industry. That's behind oil production, automotive, oil refining, and delivery and distribution. At $450 or almost $500 billion a year, semiconductors have grown in importance. And actually, a lot of industry analysts are expecting that to reach $1 trillion by 2030. So there's a good chance that it could actually move up the rankings to be number 1 or 2. And I think this has actually had some impact on the shortage that we've seen, because most of these supply chains start in, say, North America, they may pass through the UK and Europe back to Asia. And so starting from the semiconductor materials, these materials actually travel the world 3 or 4 times before they end up in a phone in your pocket, on a wearable device on your arm, or in the car that you drive. So they're well traveled, they get a lot of air miles, but the bottom line is that these supply chains are very long and complicated, and any disruption at any point in the supply chain has a major impact on the timescales and the production. And interestingly, if you do change one part of that through geopolitical moves such as trade wars, and there are trade wars between the US and China, Korea and Japan, China and Taiwan, then that disrupts a complete supply chain, which then can take up to 2 years to reconfigure to replace whichever part has been missing within that supply chain. So it is very complex, and that's why people can't get hold of the items that they're looking at. And even just taking a humble phone, if you were to look inside, it's the chips that make it work. And these are the little black boxes. Quite often the microchips that we're more familiar with, often called computer chips, these process a lot of the digital handling of data. But actually there's a lot of other chips within a phone which do sensing. There are things called MEMS, which are very tiny mechanical, electromechanical systems, which tell you which way the phone is up. So that's how your screen knows which way to orientate itself. These are all semiconductor-based materials, and the camera, the chip inside that, which is a sensing technology, the 3D facial recognition, through to a lot of the other sensors for focusing the camera, for the lighting, for the flash. All of these are semiconductor devices, and all have their own different supply chains and different technologies feeding into them. So although we talk about computer chips, it's very wide-ranging and goes much further than just the chip itself. That said, this is what a typical microprocessor, a digital chip, looks like. And if you were to look inside it, what you would see is what amounts to a pretty complex device, almost like a city looking down on it. And going back, we started life, and I'll show a slide shortly. We started with just a few hundred individual devices, transistor devices that were connected together on a single chip. But now we deal with billions, up to about 30 billion individual devices or components on a single chip, which is no larger than the size of a fingernail. And if you look at it under a scanning electron microscope, you can see hundreds and thousands of tiny interconnects and several layers being connected together to form this really complex micro city, if you like, that has to work perfectly all of the time for your computer device or your phone or any other electronic technology to work. So there's a lot that goes into that. And as I mentioned, it's been a race to miniaturize the digital components. So a transistor is a device that can be switched on and off. It basically controls the flow of electrical current. The first device made was something called a diode. But if you actually go back in history, we used to have something called valves, which looks and act pretty much like an old-fashioned light bulb. And early devices such as radios, or wireless as they used to be called, contained maybe half a dozen or a dozen of these components that could switch an electrical current. But they were large, they heated up, they used a lot of energy, and were very unreliable. Like light bulbs, they would blow after a few hours of use. A transistor is the semiconductor material equivalent of a valve, and so these can be made very small, and the real breakthrough came in the early 70s when it was found that you could combine thousands of these tiny transistors to switch a current on and off into a single chip. And the Intel 4004 was the first such device, containing about 2,500 transistors on a single chip, which was a major breakthrough. And it's been a gradual race, something called Moore's law that's been followed. It's actually not really a law, it's an observation. Gordon Moore was one of the founders of Intel and Fairchild before that. And he noted during the 80s and 90s that the complexity and the number of these individual transistors that could be integrated onto a single chip was doubling every 18 months. And that has really held out over the last 50 years. And so if you take the graph-core chip at the moment, which is a graphics processor chip, it contains at least 30 billion transistors. And those have to work seamlessly together. Memory chips contain a little less, but they're pretty much the same sort of technology, but on a slightly different branch of the semiconductor technology. So this really shows how the industry has progressed. And I must admit, I can't think of any other industry that can boast such progress over the last 50 years. And there is a comparison I've seen. You should never put an analogy too far, but back in the 1970s, around 71 or 2, it would cost, I think it was around about $1,000 to fly to the US and take 7 or 8 hours. Actually, the timing is a little less now. It probably takes to New York something like 5 or 6 hours, if you don't include 1 or 2 hours of circling over Heathrow or New York. But if it had progressed at the same rate, it should only cost something like £1 to fly there, because the economies of scale that you get from semiconductor processors going from 2,500 to 23 up to 30 billion chips, if that was applied in other industries, it would have a massive impact. And it shows how we've been able to develop technology so rapidly, from ushering in the digital age back in the 1970s through to a lot of the advanced technologies we have now. I'll touch on the markets again, and this idea that there's not a single supply chain and not a single semiconductor product. If you look at 2 forms of digital products, these are generally the memory chips that obviously store all the data within your phone, within your PC, and other places. And generally, that market is dominated by Korea. They have 35% of the global market. Microprocessors, the bit that handle the data, is a slightly different technology, but very similar to that for memory. And that tends to be dominated by Taiwan. In fact, one company in particular called Taiwan Semiconductor Manufacturing Company, TSMC. And they have around about a 30% market share globally. Other companies such as UMC and so on are very, very similar. And so the silicon market is really split between memory and logic chips. And this is for digital technologies. The US, obviously, slightly behind Korea and Taiwan. China is becoming a much bigger player. Japan has been dominant and has shrunk, but is starting to grow again. And then the rest of the world is actually quite small compared to the markets from Korea and Taiwan. So this shows the real global nature of our industry sector. And where these products are used, smartphones is actually one of the biggest users for these devices, and then PCs. Data centers, we often refer to the cloud, but genuinely it's not the cloud. The cloud is actually lots of data centers, as I'm sure you're aware. And in South Wales, we have one of, if not the largest data center in Europe. And this comprises just racks and racks and racks of digital storage space. So it's not really those white fluffy things in the air. The cloud does exist on the ground in lots of different places, and some of these are massive. They make IKEA superstores look tiny by comparison. Industrial users, consumer users, automotive and communications then make up the rest. And actually looking at it, you'll see why automotive may have dropped in terms of its prominence and importance to the semiconductor industry, because it was supplying or it was one of the major customers for semiconductor devices. And the semiconductor market used to jump whenever automotive clicked its fingers. But I think it's become less important, and having changed all of the supply chains and reconfigured a lot of the supply chains, when automotive sector underestimated the impact of or overestimated the impact of the pandemic, and then went back to the semiconductor manufacturers. They'd already switched their production to satisfy smartphones and other consumer products that had seen a sudden peak in demand during the pandemic because everyone was on Zoom and Teams and so on. So there's been a lot of disruption in the industry. I'll come on to the technology shortly, but just to give a flavour of how the world looks in terms of where it manufactures. I've mentioned TSMC being by far the largest semiconductor manufacturer for silicon chips. Samsung, again, dominates areas such as memory in Korea. UMC, Global Foundries is a US company, but out of the United Arab Emirates. And then we start getting into the other Chinese and Taiwanese players, with Intel, which has recently taken or merged with Tower, based in the US. So you see the real dominance of Taiwan and South Korea. Now, I just want to touch on briefly the evolution of the technology, because if we go back in time, then analog ruled the roost from the 1800s to the 1960s. And in many ways, analog, and some historical commentators would argue that analog is actually more real, more realistic, because the world and humans happen to be analog. But a digital representation is a close approximation. And using digital chip technology, you can manipulate ones and zeros quite easily. So it may not be a perfect representation of the analog world, but it's close enough and has really ushered in some major changes in the way that we do things. And so over the last 50 years or so, we've seen huge increases in digital technology that really have changed the way that we do everything, from our working lives to our leisure time, and industrial interactions and so on. So it's really important. And although I've said to the 2010s, it's going to be with us for decades to come. But we're now moving into a slightly different world where we're seeing new materials and new technologies coming in, and quantum will play a role in that. And in some ways, and I'm being a little disingenuous, but quantum actually is a different way of representing our analog world, and in fact can do it in a way that's quite different to digital. So I think we can see through quantum computing, but also some other activities such as cybersecurity, something called quantum key distribution, through to atomic clocks that will be used for a whole range of activities, including positioning and autonomous drive and so on. Then we'll see a different representation of the world. But I think for a long time to come, we will see digital and possibly quantum working together. And we can't rule out analog, because a lot of the technologies that are used today, sensing, for example, sensing the world in which we live, as I said, it's an analog world, and the sensing technologies take that analog world and convert it into digital. So there are things like radio waves, dealing with radio waves, dealing with sensing, which is optical, and power management, which is important for electrical vehicles and sustainability. These are still analog applications. So we shouldn't lose sight of the fact that analog, digital, and quantum will work hand in hand. And that digital is just one way that's allowed us to represent the world over the last 50 years or so. And I'd like to think that one of the ways that we're moving forward is through the materials technology. I keep mentioning silicon, and silicon chips have been around now for the last 50 years, but it's managed to evolve through miniaturization by following Moore's law. And that miniaturization is getting harder and harder as we reach some of the atomic dimensions. And it means that we need to switch to slightly different material systems to be able to continue with Moore's law, but also to make use of some of the sensing and other applications that we need in semiconductors. So it reminded me that we've always referred to the importance of materials in human evolution. From the Stone Age and the Bronze Age, we talked about the tools that were important to our evolution. And in fact, you could argue that silicon and the technologies we have today are just tools that we're using in our everyday lives. So I'd like to think back that, or that we'll look back in 100 years' time or thousands of years' time on this being the semiconductor age, who knows, the silicon age, the compound semiconductor age. A little bit doesn't trip off the tongue too easily, but I think there's scope for that in the future to stress the importance of the technology. And I would say that it's not necessarily a modern thing or a new thing. The properties of semiconductors were known back in the 19th century. And some of the properties of being able to detect light and convert light from energy or to energy was discovered around about 1821 using lead and sulfur combinations. And there were other materials such as selenium that it was known could detect light and convert it into a current or something you could measure. You could measure the voltage of. So materials properties are not completely new. Harnessing and being able to manufacture and use them is something that we've really progressed on over the last 20 years or so, or 50 years or so. But if you look at even communications, we had Samuel Morse sending his first telegraph message back in 1844. And I think sometimes we don't celebrate these things enough. One of the first messages sent by Marconi, for example, was here in South Wales from Levenok Point out to, I think it was Steepholm, but it could have been Flatholm. Steepholm would make more sense. In the US, it was about 2 years behind Marconi that the first transmission was made. Sorry, it's 2 years before Marconi. The first transmission was made to a ship off the coast of Northern California in San Francisco from a place now named as Telegraph Hill. It's unfortunate that we don't celebrate in the same way by naming things like Telegraph Hill or Telegraph, I guess in Wales it could be Telegraph Dyke just down the road. But we tend not to celebrate these technologies. And I'm also reminded of how we don't really anticipate what could happen in the future. And if you watch TV now, you talk about autonomous cars, driverless vehicles. You'll often see commentators say, yeah, you won't get me in one of those things. But actually, when you look back in maybe 10 or 20 years' time, you'll realize that actually we just adopt these things very quickly. And I do like this quote that one day every town in America will have a telephone, which I guess you could argue is correct. But you know what was being thought of at that time. And the adoption of new technologies tends to take quite a long time. So although semiconductors have enabled things to move more quickly, what we've seen is this rapid adoption of new technologies. So going back to the telephone, it took 50 years for it to reach 50 million people. Electricity was 46 years, television 22 years, then you get down to ATMs that a lot of people thought wouldn't work, 18 years for it to reach 50 million people. Mobile phones, 12 years, and we're now down to just a few days for things like new software applications and so on. I'm not saying this is a good thing. I'm just observing that the adoption of new technologies, and in this sense, to reach 50 million people is rapidly shrinking. And it's interesting that someone called Amara, who was an American visionary, made an observation that we tend to overestimate the effect of a technology in the short run and underestimate the effect in the long run. Now, I mention that in terms of semiconductors, in that quite often, if you work in the industry, people keep thinking that, oh, yeah, autonomous cars, they'll be here next year or the year after. Actually, it takes a little longer for them to penetrate and to have some sort of impact. But then when you look back, and I guess the same applies to digital photography. people couldn't see that, or a lot of people saw that coming quite quickly, but actually it's only when you look back, you realize how quick it was. And the same in the move from cathode ray tubes to flat screen TVs. So once the technology is adopted, it feels as if it's been with us for a long time. The first smartphone was the iPhone, which was launched in America in 2007, in the UK in 2008. So we're only talking about 14 years ago, and yet many people will think it probably goes back to the 1990s. The tablet, such as the iPad, was launched in 2010. So these are all in the overall scheme of things, actually quite recent developments. So it's sometimes easy to lose sight of that. And when we talk about autonomous vehicles now, I'm sure that people in this photograph would have heard of the motor car. In fact, I think there is one buried in there somewhere. And they would have thought, yeah, but that's never going to take off. You're never going to see. In fact, people said that about the internet. It's never going to take off. People will get bored of it. And what we find is that, yeah, not sure it's a good thing, but you look around, you don't see many horses and carts on the road now. One or two, but actually people get in their cars to go to ride their horses or to watch horse racing. And that's how quickly these things develop. What's that got to do with semiconductors? Well, all of these technologies have really been enabled by semiconductor technologies, whether it's the digital age or increasingly healthcare technologies, wearable devices, and so on. But it's now moving towards atomic engineering. And I've mentioned the materials side of things. If we look at the sort of markets that are enabled by technologies, right in the center, hidden almost from plain sight, are semiconductors, whether it's silicon-based or, and I'll come on to compounds in a second, but compound semiconductors. But I've already said that these supply chains are very complex and very long and fragmented. So we're all familiar with the end products, such as the data centers, healthcare technologies, AI, robotics, energy systems, sensing technologies, 5G connectivity we're using now. This signal is coming to you by a combination. If it's over the airwaves, then it's coming through compound semiconductor devices, generating the radio frequency elements that are needed to transmit to and from a handset. And the fiber optics, the digital technology that's beaming the lasers through an optical fiber cable is coming through compound semiconductor devices, and probably hundreds and thousands of them around the world. So all of these technologies are pretty much dependent on semiconductors and compound semiconductors, but they're so far removed from our end device that we don't even think about them, which is why they seem to be mysterious. So bringing up the periodic table of elements created by Mendeleev, I'm sure we're all familiar with this, and I didn't put this on right at the beginning because this is the point where everyone glazes over and switches off. But essentially, I just want to talk briefly about elements such as germanium and silicon. These are semiconductor materials. And essentially, at one end of the periodic table, over on the left, we tend to have metals, and on the right, we tend to have the non-metals. And so one side of the table conducts electricity quite well, the other side doesn't. In the middle of the table, and it's traditionally called group 4, you have elements such as silicon and germanium. Germanium was the first material used to make a transistor device, but silicon is much cheaper and more common. These sometimes conduct, sometimes they don't conduct electricity. And that's why they can be very useful for digital technologies, because essentially you can switch them on or switch them off by controlling the way a current flows or doesn't flow. And so that property was discovered back in 1947 at what became Bell Labs. But essentially that was the first transistor, and it was pretty much ignored. No one really saw the relevance of it until we started to combine many transistors on a single chip. And silicon remains the most common of all the semiconductor materials. But what we have now, and Wales is a leading player in these technologies, is something called compound semiconductors. And these are combinations of elements at the atomic level that are pulled together in very precise ways in order to achieve what silicon and germanium can achieve in terms of switching on and off, but also to be combined to provide other properties that you can't achieve with silicon alone, such as light emitting light or receiving light and doing something with it, converting it to energy or to a signal that can be converted to electricity. Then by taking elements from group 3 and group 5 of the periodic table, and even group 2 and group 6, then combining them in a very careful way through atomic engineering, you end up with the same properties of silicon, but then going far beyond. So these are materials such as gallium arsenide, gallium nitride, indium phosphide, indium and gallium antimonide, and various combinations in between. And what this does is allow you to manipulate the properties of those materials in order to sense light, switch on and off very, very quickly. For example, silicon is used in devices that switch at 3 gigahertz, which is 3,000 million times a second, which sounds pretty fast, but with indium phosphide, you can switch at 760 gigahertz. So these are not small incremental jumps. These are major, sort of more than 10 times or hundreds of times faster than silicon, which for new and emerging technologies, and when we go to 6G and beyond, will be absolutely necessary. And compound semiconductors are used for a lot of next generation materials. They're not generally in place of silicon, although they could do what silicon does. You wouldn't need to spend the higher costs to just replicate what silicon does. But these offer properties that go way over and above what can be achieved with silicon. And this includes things like power control, inverters that convert from a DC current to an alternating current, for example, to convert from battery to effectively higher power applications for motors and drives, and for energy efficiency to achieve net zero targets. I've already mentioned speed for connectivity. We want our data faster and faster, and no matter how fast it is, it's never fast enough. So we'll go to 5G and beyond using compound semiconductors. And then for receiving, converting, and using light for optical or photonic applications, then compound semiconductors really come into their own. There is a technology called silicon photonics, which essentially combines compound semiconductors and silicon so that you can have an optical device that then has the switching capabilities, the digital capabilities of silicon. What not many people know is that South Wales is home to the world's largest cluster of organisations, from universities through to manufacturing facilities in compound semiconductors. And that's been recognised by the likes of MIT, but generally around the semiconductor world. And as I said before, it's very much a global industry. But we do have world-class research in the form of Cardiff and Swansea universities, the Institute for Compound Semiconductors, which is based at Cardiff University, and at Swansea, the Centre for Integrative Semiconductor Manufacturing. We also have facilities such as the Compound Semiconductor Centre and also the CSA Compound Semiconductor Applications Catapult in Newport. And then we have companies such as IQE, Newport Wafer Fab, or Nexperia, Microchip, and equipment manufacturing with a global footprint in the form of KLA, based in Newport. So around along the M4 corridor generally, but we're hoping that we can expand with either direct investment from overseas or from startups within the region. So a lot of activity going on. And I'd like to stress again that the silicon industry is by far the largest globally. This is really used in digital applications, so microprocessors, memory, MEMS, the microelectronic mechanical devices, And that is around about a $450 billion global industry. Compound semiconductors, although much smaller, is growing in proportion. And these are generally for non-digital applications. So generally analog or quantum applications, although they can also process digital data. And this is around about a $50 billion industry, and it's often referred to as either, it could be the 2635 industry, gallium nitride, gallium arsenide, or indium phosphide industry. These are the base components that are used for atomic engineering. And just to give an idea of how the materials are made, whether it's silicon or compound semiconductor, you actually start off with a molten bath of material, if you like, at several hundreds, if not thousands of degrees centigrade. And then a seed crystal is dipped into the molten material, and then it's gradually pulled out. And this could be over several hours or even days. And it's twisted as it's pulled out, and it grows into what's called an ingot. And this ingot is, I don't really know how to describe it, but essentially it's this long cylinder that can then be cut up and sliced. These slices are then polished, and these become what are known as wafers, which are the starting materials, or sometimes substrates, that are the starting materials on which the semiconductor structures are built. And if we look at a typical compound semiconductor material, there's a process called epitaxy, which comes from the Greek word epi, meaning surface, and taxi meaning one of those things you can't get hold of on a Saturday night. Taxi means on the same axis, so it's the same atomic axis, which means that the end result is a single crystal where all of the atoms are perfectly aligned, rather than if you were to spray paint and it becomes a random mixture or amorphous compound. These are pure crystalline structures. And some of the materials that are produced using the EPI process at places like IQE in South Wales are several hundred layers, and each of those layers may be just 2 or 3 atoms in thickness, but they have to be precisely controlled and completely predictable. And so that's the sort of things that we produce here in South Wales. The substrates get what's called fabricated, which is the process of going through photographic masks where there's a layer of something called photoresist, which is then exposed to ultraviolet light. It could be written directly by an electron beam to very fine detail that produces those structures I showed very early on that you can only see under a scanning electron microscope. The fabrication process is done in places called fabs. So although fab is quite often used as a phrase in Wales for something that's very good, it's also used as a fabrication plant or a manufacturing plant for silicon and compound semiconductor products. These then get cut up and packaged by companies such as Microchip that we have in Wales, and then they're assembled onto circuits. Now, this often happens outside of Wales, so these chips could be produced here and then they travel around the world, and then eventually they come back into our pockets in the form of devices such as phones. But even breaking down something that apparently is quite simple, like a camera, you would be amazed at the number of components and subcomponents, including quite a few different semiconductor devices that go into just that simple device. So essentially, anything that needs energy, speed, or light will use compound semiconductors. And these then feed into end markets such as healthcare technologies, gaming, energy, transport, space, and security. And the sort of areas these are used, I won't go into the details now, that will be in the test paper for later, but vertical cavity surface emitting lasers is a form of a laser that's a recent development, but Wales leads the way in. And that's used for 3D sensing, proximity sensing, time of flight for camera focusing, micro LEDs, and so on. Gallium nitride, used for radio frequency, for transmission and receipt of radio waves, amplifiers, filters, systems on chip. These are all, again, compound semiconductor materials based. or can be, and a lot of other lasers and sensors used for infrared cameras, night vision, and thermal imaging. I won't go through all of these in detail, but this really just shows the scope of where compound semiconductors are used in a whole range of things, from electric vehicles through to security. So it's very wide-ranging, and as I said, Wales is perhaps surprisingly a world leader in everything from the materials through to the packaged devices that then are built onto the circuit boards that end up inside whatever the device is that you have. I've talked about the global supply chains. It's interesting that a lot of what we produce in the UK, and Wales in particular, goes to North America and Asia. Ironically, the stuff that gets shipped from Wales to North America often ends up in Asia, which then we tend to buy back. So a lot of the products you have in your pockets have probably started life in Wales, but then have been around the world a few times. And I mentioned California as being the home of the semiconductors back in the 1960s and 70s. A lot of that work migrated to Korea, Japan, and Taiwan. But actually, the industry, because it favors clustering and close collaboration, what we have in Europe, largely around anchor organizations such as ST Microelectronics, Infineon, Siemens, and Philips, as they were, have clustered around Grenoble, Leuven, Eindhoven, and Dresden. But we do have this cluster in South Wales that would be the 5th European cluster, or the world's first compound semiconductor cluster. And that's something I think we should be rightly proud of. And these organizations, from universities through to manufacturing, are all clustered around a 60-mile radius within, or less than that actually, 30 or 40-mile radius around South Wales. The evolution of the cluster is quite old. Most of the organizations have been here for at least 30 to 40 years, but it's really only in the last 5 or 6 years that we've started working together. And that's largely when we found that products produced by one company were being shipped around the world, only to come back to be processed by another company in the cluster. And we weren't aware of that. So the same thing happened with devices that were being sent to customers, and they were sending back, for example, to Cardiff University to be tested. So once we discovered that, we felt that the sum of the parts was greater, the combination of what we were doing was greater than the sum of its parts. So we started working together on a number of collaborative projects, and we have been doing so for the last 6 or 7 years. And that's given us a very strong position. And we believe that the private-public investment to date is around about $1 billion. So that is pretty impressive for quite a small area that no one's heard of. Nice thing is, when we travel around, most of the conferences are in either North America or Asia, and a lot of the delegates are from global locations. And many of them have heard of Wales because it's famous for compound semiconductors. So thank you very much for your time. I've been speaking non-stop, so if there were any questions, I'm sorry I didn't give you a chance to look in, but if there are any questions now, I'm happy to take those. Thank you.
Thank you so much, Chris. That was a really fascinating presentation. You gave us a really comprehensive overview of semiconductors and compound semiconductors, and that was really great. Thank you.
Thank you.
So I can't see anyone having posted any questions in the chat, but feel free to do that. And whilst we give opportunity for that, there was a couple of things that I would like to ask you about, Chris. So obviously semiconductors and compound semiconductors is a growing kind of sector across the globe, and also particularly in South Wales with the CS Connected cluster. So what sort of skills do people need to move into the sector? And then also, what sort of prospects are there for them to kind of career prospects to support their skills development, once they're in that sector, Chris?
Thanks, Kate. Mostly, I mean, the sector has a lot of roles that are not all technical. So like any other business or research establishment, there are admin, finance, HR functions. There's a whole range of areas that don't interact directly with the technology. Most of the engineering and management roles tend to be from backgrounds in science and engineering. So it could be physics, material science, chemistry, electronic engineering. But actually, there are quite a few staff that have come through different graduate approaches, including English literature and a whole range like that then develop, because they've got, particularly if it's analytical skills, then they can develop the skills that are needed within the industry sector in particular. But over the last 3 or 4 years, we've focused on putting together modules from school leaver qualifications through BTEC qualifications and MSc master's degree qualifications and modules. One has been developed and implemented at Swansea University and 2 at Cardiff University. And we're lucky that Cardiff also is home to the Centre for Doctoral Training, which focuses on semiconductors and in particular with a sub-focus on compound semiconductors. And I think across the region, we actually have a lot of opportunities to undertake the relevant courses that would make candidates really attractive to not just the industry partners, but to further down the supply chain that are moving in, and also within the research and the prototyping facilities, all heavily recruiting and actually all seeing very high demands. And although it's not always a good thing from an industrial point of view, one advantage of a cluster is that if people are moving into the region to develop a career and to look for jobs, then they're not just restricted to one organization. There are, a couple of dozen organizations that are using those same skills. And that's the real advantage that Silicon Valley had, in that people went there because they knew that they could develop their career over a long period and perhaps get experiences in different types of organizations. And that's one of the things, although we don't necessarily from an industrial point of view, you don't want to encourage job hopping. It does allow to gain a wider perspective on how the industry works. And I think that's a real advantage of clustering. And that's one of the reasons that the semiconductor industry, because of the need for the high skills levels, has formed in clusters whenever it's started out in California, same in Asia, and as you saw earlier in Europe. So I think we have a good basis for it, but the number of jobs is expected to grow very rapidly over the next 3 or 4 years. So recruitment will become a key element. And so the opportunities will grow with that.
And I also understand, Chris, that within the sector, I think sort of average salaries and things are quite significantly higher than sort of the local sort of economy in South Wales. Is that correct?
Yeah. There's actually a report on the csconnected.com website that can be downloaded, which is an annual report which analyses the impact of the industry sector on employment and on the value added to the region. And that can be downloaded, as I say, from csconnected.com. But the average salaries tend to be much higher than the average for manufacturing as a whole. And in many ways, that reflects the high qualifications, a lot of graduate employment and a lot of postdoctoral employment within the sector as well. And sorry, I forgot to mention, of course, CPD as part of the offering. Kate is working on some CPD activities for either people that may be transferring into the industry from other industry sectors, or to upskill existing employees within the region.
Yeah, that's right. So we're kind of working on a program of CPD opportunities, as Chris mentioned, at the moment, to help kind of people, upskill within the sector, but also kind of maybe reskill from related sectors like engineering and fields that perhaps might have been made, people perhaps might have been made redundant through the pandemic or things like that, that there's opportunities for them to transition into the sector. So that's really, really great as well. So really, I think the message there, Chris, is that kind of there's opportunities for everyone, from people school level through to kind of people who've done sort of MScs and PhDs, and there's opportunities for career prospects and growth within the sector and within the cluster in South Wales. So yeah, no, that sounds great.
Excellent, thank you.
Just a final question actually from me. So I also wanted to I think you touched on it in the presentation, but I think it's particularly interesting to kind of think about how semiconductors and compound semiconductors are contributing to society and some of the real pressing challenges of today, like things like climate change and AI and stuff like that. And I just wondered if you could sort of elaborate a little bit more on that, Chris.
Yeah, absolutely. In terms of things like healthcare technologies to address an aging population, it all puts extra pressures onto various health services around the world. And diagnostic tools, such as those being developed within the cluster region, are likely over the next 10 to 20 years to become commonplace. So wearable devices, such as what we have at the moment, are quite limited in what they can do. In future, we'll be able to use optical sensing using compound semiconductors to identify everything from cancer markers through to glucose levels for diabetes control. And actually, in another project within the region, there's a development of something called microneedles, which is a patch that you can wear for insulin injection. And so you can automatically monitor things like glucose levels and then adjust the insulin throughout a 24-hour cycle. But the key there as well is in there's something called white coat syndrome. When you go to the doctor, your blood pressure is high because you're at the doctor's surgery. If that can be measured and monitored 24 hours a day, 7 days a week, then it can then monitor exceptions, so when things are particularly out of control, and that data could be aggregated, and then it could send alerts, which means that early action could be taken for preventative measures rather than for surgery and remedial measures. So I would like to hope that over the next 20 or 30 years, we'll see this shift from remediation to prevention, which will really help with an aging society and with the pressures on health services. When it comes to sustainability, inverters that I mentioned from earlier, these are absolutely necessary in electric vehicles. It's the way you're going to get your mileage up, because battery anxiety is a big problem with electric vehicles right now. And by using smaller, lighter semiconductor products that are much more efficient at converting energy, that's one way that we'll be getting range increases in electric vehicles, but also getting the weight of the vehicles down at the same time. But inverters are also important components in converting energy from solar systems, even wind farms and tidal energy producers. And so making them even lighter is something that's critical. And I don't want to advertise Amazon, but I noticed recently that if you look at look for power supplies to convert to USB outputs, you can actually search for GaN, G-A-N, which is gallium nitride. It's being sold as a marketing tool because they are much more efficient at converting energy. If you plug in something to charge, you'll notice the charger often gets hot. If you use a gallium nitride charger, they're more expensive at the moment because compound semiconductors are, but with volume, price will come down. But if you use a gallium nitride charger, you'll find you can leave it on all day and it just won't get warm at all. And the importance there is not, you may want that during the winter, but actually it's a waste of energy. It's a very inefficient way of producing energy. And so from net zero targets, materials, compound semiconductor materials are essential, healthcare technologies, robotics, AI, you name it, all these things that will lead to societal changes, hopefully for the better, will come because of compound semiconductors.
That's really great, really exciting, isn't it? You know, and great to think about all the future opportunities there. So
I think great opportunities, yeah.
Thank you so much, Chris. Well, we haven't got any other further questions, so I'm going to draw that to a close today. Thank you all for joining and listening. And as I say, this will be available on our YouTube channel. And all I'd like to say is thank you very much, Chris, and we'll sign off.
You're welcome. Thank you.
Bye-bye.
Thanks very much. Bye-bye.